P1, we're taking a look at learning test number 3, where we are going to go and calculate a bunch of transformer values. And we're going to go and use those ratios that we were given there before. This is going to be our super important one. VA in is equal to my VA out. And then we're also going to go and use the NP over top of NS is equal to VP over top of VS is equal to IS, the current is flipped, over top of IP over here. We're also going to go and create a new formula that we haven't dealt with yet, and it's going to be very important later on once we start getting into auto transformers and taps transformers. And what it's going to be is it's going to be this thing called a volt per turn. And literally, it's going to be us taking these two over here, and then we are going to go and cross multiply NP down to the bottom, and we're going to go and cross multiply VS up to the top. And what that's going to go and give us is this ratio where it's going to be my VS over top of NS is equal to my VP over top of NP. What you should note about this is that the number of volts that I generate per turn of wire is going to be the same on both sides of the transformer. This can really help us, get to some of our auto transformer and multi-tap transformer values later on, where we just establish a volts per turn, then we just count the number of turns and multiply that back out. Let's start with our very first one. Example number 1, what's the volts per turn of a transformer if I've got a rating of 480 to 120? If my high voltage winding contains 200 turns. Well, I just identified what is my high voltage side. That's going to be this side and this side over here that are both identified. And then I just go and place them into a division. 480 divided by 200. 480 volts over top of 200 turns. That's my primary sides. Gets me to a value of 2.4 volts per turn. Based upon that, how many turns would there have to be in my low voltage winding? Well, I'm going to identify my low voltage with this over here. I don't know much other than my VT, volts per turn primary, is equal to my volts per turn secondary. So it's the same 2.4 volts per turn that I'm going to go and have. What I could do is I could just go and divide that out. If I know the number of volts per turn on my primary, that's what they're doing, is they're taking this thing here, ES over top of NS, volts per turn of secondary, is equal to my volts per turn of the primary, but at this point it's 2.4, right? We've calculated that in the previous question. All that they're going to do now is they're going to go and cross multiply this NS up to that side and this 2.4 that we calculated down to this side over here. So I take my secondary value of voltage, 120 volts, divided by that 2.4 volts per turn, which gets me out to a value of 50 turns. This makes sense if we take a look at our values of voltage, right? If I take a look, it's a 4-to-1 ratio. 480 divided by 120 is 4-to-1. There should be a quarter of the turns, 200 divided by 4, that I'm going to go and see on my secondary side. Example number 3. They say a transformer has 300 turns on the low voltage winding and has a voltage rating of 208 to 240. How many turns are going to be required on the high voltage winding over here? Well, the high voltage winding should have a few more turns than my low voltage winding. We know that through our ratios. So now it's just a matter of working off of what we have over here. So we've got this number of turns on the primary, number of turns on the secondary. We're going to drop values in for what we have, but first we're just going to move this formula around. What I'm doing is I'm multiplying NS up to a top, then I'm going to go and take EP down to the bottom, and I'm going to take ES up to the top on the other side, which gets me to this formula over here. Once I've got it laid out as a useful formula, I'm going to plug in the values that I already have. I know that I have got a secondary voltage, right? We are going to 240 volts on that secondary side. We have got 300 turns. That is going to be on my low side. We have got 208 volts. That is going to be on my low side, right? These are my low sides over here. The voltage rating that they've given us over here talks about which side is my primary that I'm feeding in. The first one over here, 208, which is my secondary. That's why they've chosen these as those values. To be honest, they could have, interchanged it as well. They could have done the opposite way. We would just change the formula, but we'll get to the same answer either way, which is going to be this 346 turns. Does it line up? Absolutely. The higher voltage side, 240 volt, should have a few more turns than my lower voltage side, 208, which has only got 300 turns. Example number 4, a step-down transformer with a voltage rating of 600 volts dash 240. So it's step downward. That means we're feeding in as my 600 volts is going to be my primary, my 240 volts is going to be my secondary. Has a primary current of 10 amps. Well, if it's 10 amps, that means that that's going to have to be in the 600 volt side. What is the impedance of the load connected to the secondary? What we're going to do is we are going to go and carry through our current to the other side. Once we carry through our current to the other side, then we can go and figure out what we've got for our impedance. So we'll just draw this out over here. This side over here is 600 volts. We know that it has got 10 amps over here. This side over here is going to be 240 volts. And we know that, well, we don't know much at all. We just know that what we've connected to this side over here is some sort of an impedance that has caused current flow, which has caused current flow over here on this side. Let's take a look at what we have. We know that VA in is equal to VA out. Now they're going through a formula like that. VA in is equal to VA out is just another way of rewriting the same one, but I prefer to work inside of power because it's less common that you're going to screw stuff up. So we're going to go and take 600 volts times 10 amps. That's a form of power, right? VA, which gets me to 6,000 VA on this side, which would mean that on this side, I must also have 6,000 VA. And if I've got 6,000 VA, I can divide it by its value of voltage, 240, which would then give me my value of current. You can take a calculator, take 6,000 VA, divide out your volts. It's going to go and leave you with 25 amperes. Does this make sense? Absolutely. I've got the high voltage side with a low amount of current. I've got the low voltage side with a high amount of current. That's the way that a transformer inherently operates. If you go back to those early transformer formulas, you see that the current is always going to be opposite to the voltage that we are going to have. So we've got 25 amps over here. What is my impedance that I have over here to generate that? Well, R is equal to E over I. We're going to go and use the impedance form of that, where R gets substituted by Z, and then E over I gets substituted in here. We see that we've got 9.6 ohms that I'm going to go and have over here. Here's where we're going to go and pause for a second. We're going to do a little bit of extra math that was not inside of here. We're going to talk about what is true impedance versus what is seen impedance that we are going to go and have. We said at the very beginning of second learning task that it changes the seen value of impedance. What is the actual impedance? Well, we just calculated that as being 9.6 ohms over here. What does this source see the impedance as being? Well, we're going to have to go and do the same calculation where we would take the value of voltage over top of the value of current. In this case, I have got 600 volts over top of 10 amps. R is equal to E over top of I. So if I go and take E over top of I, what I'm going to go and see over here is that I have got a seen impedance. I'm going to stick it in a little thought bubble here to go and kind of differentiate it. I'm going to go and have a seen impedance that is going to go and be 60 ohms. Do I actually have 60 ohms in the circuit? No, I've got 9.6. But it's the way that it changes through here. We're seeing a ratio going across from one side over to the other. What is my transformer ratio, by the way? The differentiation between my high side and my low side, well, let's just go and punch that into the calculator. One sec here, just opening up that calculator there. And drag the thing all the way in here. So we're just going to go and figure out a ratio, 600 to 240. Calculator one there, 600 divided by 240. Tells me that I've got a ratio of 2.5 to 1. Does this impedance here, the true impedance on this side, match up to this one by a 2.5 ratio? I don't know. Let's go and try and punch it in there. Well, I do know, but I'm pretending I don't know. 2.5 multiplied by 9.6 gets me out to a value of 24 ohms that I'm going to go and have over on this side. Now, wait a minute. Does that work out at all? Absolutely not. What is the actual relationship? The actual relationship is going to go and be my ratio that is going to go and be squared. This 2.5 ratio that we had, which was my transformer ratio, high side over to low side and low side up to high side. If you take a look, currents are a 2.5 ratio. Voltages are a 2.5 ratio over here. But the actual resistance that I'm going to go and have across from one side over to the other is going to be my ratio squared that I'm going to go and have. Take a look at 2.5 squared equal to 6.25. And 6.25 multiplied by the 9.6 gets me out to a value of 60. We're not going to work with that, okay? You should see that there is a relationship. It is all mathematical. If you go through and expand out your Watt's law and your Ohm's law, you will be able to go and prove this squared ratio relationship. What I want you to pull out of what we have just done here, though, is the fact that there is relationship to my impedance across from one side to the other, and that my transformer doesn't change the impedance, but it changes what my source sees. My source sees this 9.6 as a 60 ohm impedance over here. Transformers themselves can only change values of volts and currents. They cannot change impedance. Impedance is going to be a physical build, right? We know that XL is based off of physical. We know that R is based off of the physical build. We know that Z is the vector sum of those. So the transformer does not go and change resistance. It just changes the way that we see resistance. All right. Example number 5. If the transformer in example 4 has a secondary load with an impedance of 5 ohms, what current would go and flow in my primary windings? So they're taking that same transformer that we just had over there, 600 volts primary, down to a 240 volt secondary. It's a step down application. They're taking off that original load. They're replacing it now with something that is going to go and be 5 ohms. Over here. What do I know? VA in is equal to my VA out. Can I go through all of these forms over here? Absolutely, I can go through all of those forms over there. What they're doing is they're finding the current on this side using the resistance and the voltage. They find the current, and then they're going to go and take the current and they're going to go and move it across to the other side through manipulating that formula over there, which is then going to give them their primary. That's their method. It is mathematically correct. It is entirely doable. It could be your preferred method. I prefer to work with power because it's just going to make more sense when we're into electronics. But VAN is equal to VA out. Can I figure out my VA? Absolutely. I can just use my E squared over top of R. 240 squared over top of 5 ohms is going to go and give me a VA. Let's do that. 240 squared divided by 5 gets me to a VA of 11,520. If this side over here is 11,520 VA, then I know that this side over here is also going to be 11,520 VA. And if I take a VA and I just divide out my volts, we'll divide it by 600 volts, we're going to go straight to our current. So we're just going to do that. Divide it by 600 gets me to 19.2 amps. As with pretty much anything inside of our calculations world, there are multiple ways to go and work our way around to stuff. Some ways are really easy, some ways are harder, some ways cause confusion, some ways are going to be simpler. You got to pick, you got to experiment with all. Don't just take my word for it that, power is what works best for everybody. You might not be the person, you might be the anomaly, okay? If you're the anomaly, you wouldn't know that, though, unless you try the other methods as well. So search through till you find a method that works for you. All right, let's go talk about a high voltage one. Over here, we got a 12 kV transformer that is rated at 100 kVA. Determine the current ratings of the high and the low voltage windings. Now, this is a very common way that we are going to go and get given transformers, right? We don't get transformers that are going to have, oh, actually, we haven't covered that yet. Surprise! We will cover this in a minute, but transformers do not have an amperage rating because the amperage is all going to be based upon the amount of load that we are going to go and have connected to it. If I've got a transformer, it's going to be rated in kVA. Total amounts of volt amps. If it's K, that means thousands. This over here talks about my voltage rating of it, and what I'm going to be able to do from this is I can figure out the maximum. I want you to go and write that word over there. Determine the max current rating of the high and low voltage windings. In other words, they will not, I repeat, they will not necessarily be carrying this current at all times. They could, if we load up the transformer enough, but it doesn't mean that they always will be. Okay, so just don't think that way. Let's find out what those maxes are going to go and be. Well, for this, we're given that really, really handy VA. VA in is equal to VA out, so both sides are going to be 100 kVA. 100 kVA on the primary. If I take my 100 kVA and divide out my voltage, 100,000 divided by 12,000 gets me to 8.3 amps. A tiny, tiny amount of current. High voltage, lots of insulation, but it's going to be a tiny amount of current inside of a tiny wire. Now, that is going to be its absolute max that it's going to go and put through at fully rated. You know, you could overload it, but for what it's rated, that's the maximum we could go and do. The low voltage side is going to be 100,000 VA over top of 440 VA, or 440 volts, which tells me that the maximum that this thing could be putting through over here is going to be 227 amps. Okay? That's once again going to go and be a maximum. Now here's where we have to go and explain some stuff that's not inside of the book. We've got to deal with some misconceptions that students commonly have. Probably you're one of them that has got this bad misconception in your mind because we've done these transformer things, and you may have heard somebody tell you before that, look, if the current goes up on the one side, the current goes down on the other side. It is not a teeter-totter. You cannot treat current as a teeter-totter. What the teeter-totter analogy is, it's a terrible analogy, but it's kind of used to go and describe stuff sometimes. And people think that if I've got IS and IP, that if my current goes up on this side, then my current is going to go down on this side. What that would mean, if I actually carried that all the way through to its terminal end, this concept would mean that if I would just keep increasing my secondary current, I would eventually be able to get down to a primary current of 0, right? I mean, there's only so far you can go before you're going to go and get down to a opposite value. What actually happens is that my primary current is a reflection of the secondary current. It's a smaller reflection of it, okay? That's all that we need to go and treat it as. Not that it's necessarily going to be going down when the other goes up, but that it's a smaller reflection of it. We need to deal with this right now before we get ourselves into, hot water off of these things later on. Let's draw out a transformer. We're going to draw this transformer out because we've got these maximums that we have over here. I've got a high voltage side. It's going to be 12 kV over here. I'm going to go and have a low voltage side. This thing is going to, I'm just going to draw fewer windings on it just to represent that it's a smaller one, 440 volts. Okay. VA in is equal to VA out. We are 100% convinced of this fact. We've done the math off of this one, and if you don't believe the math or just skip past those videos, some of you did, don't do it. But if you did, then, you would have been like, yeah, VA in is equal to VA out. Tell me, right now, if I go and connect this thing onto my 12 kV lines, okay, so I've got this thing attached to my 12 kV incoming lines over there, and I've got this side over here that is also set up. But if I've got this thing open right now, will I have volts over on this side? Absolutely, I will have some volts on this side. I'm going to get that 440 volts. Will I have current on this side? Well, if I've got no load connected, my current would, at this point, be 0, right? Which would mean that if I've got 0 VA, or 0 amps, I can multiply my amps by 440, therefore I'm going to go and have 0 VA. Which would mean that this side here would be 0 VA as well. If I take 0 VA divided by 12,000, I'm still going to be at, a value of 0 off of that one. So I would see that I've got 0 amps in the secondary and therefore 0 amps on the primary. In reality and practicality, because this is still theoretical transformers here, there is some resistance. There's a little bit of magnetizing current that will be set up. But we're ignoring that for now just to go and deal with this concept. Okay, we will hit that point where we're going to go over the practicalities. This is all conceptual still. Let's take a resistance and place that resistance across here. As soon as I place a resistance across here, is there a path for current flow? Well, yes, there is. Okay, how much current is going to flow? Well, we all say, well, I don't know. Tell me what the value of resistance is, and I'll calculate it for you. And I'm like, okay, fine, I will. Here's my value of resistance, 440 ohms, okay? So if I've got 440 ohms, I know that I can calculate my I. I is equal to E over top of R that I'm going to go and have over here. So if I go and take 440 volts, divide it by 440 ohms, I see that then, well, oh man, look at that. I've only got 1 amp of current. Does that 1 amp of current get supplied magically, or does it come from this source through the process of transformation? Absolutely, it comes from that source, so it's going to have to be supplied on this side? Absolutely. So what I can do is I can just create my VA. I've got 1 amp current, 440 volts, therefore my VA is 440 VA, and VAN is equal to my VA out, so this is also going to be 440 VA on this side. I'll divide it by 12,000. Find out what my current actually is. Divided by 12,000 equals 0.36 amps. So 36 milliamps. Literally, that's all that I'm going to go and see on this side. 36 milliamps over here. So we have 36 milliamps and 1 amp that we're starting out at on both these sides. I'm going to graph these two against each other. IP, and then we're going to go and have IS, and we'll just go and graph these things. So right now we start out at value 0. We rose a tiny little bit on my primary, right? We started at 0. We went to 36. I wrote 3.6, but it's 36 milliamps. And on my secondary side over there, we started at 0. We went to a value of 1. We saw that they both rose at the same time. Let's go and drop this value of resistance over here. I'm going to go and drop this thing down to 220. I is equal to V over R, so if I've got 440 volts over 220, that means that now I'm going to go and be at a value of 2 amps. No, that's way too little. Let's go and drop this thing all the way down to 22 amps, or 22 ohms, okay? 22 ohms, if I go and take 440, divide it by 22, I'm going to come out to that I'm now pulling 20 amps through this side. What's my VA? I don't know. We can calculate that. We just go and take 440 multiplied by 20, which is going to go and get us to 8,800 VA that we've got, which would mean that my primary side would also be supplying 8,800 VA over here. That 8,800 VA that I'm going to go and have is going to result in current that's going to go and flow inside of here. How much is it? I don't know. We'll just take a look here. We'll say 8,800. My VA divided by 12,000, my voltage, oh, that's too many zeros there, equals a value of 730 milliamps. Has the current gone up? Absolutely. It was just at 36. Now we're at 733 milliamps. And so we can go and graph another point on both of these. And what we see is that as my secondary current goes up, my primary current goes up. But it's just measured on a different scale. That's all that's happening inside of here, okay? The fact that this current went up did not somehow make this current go down. This current wasn't starting out on my high side. It didn't start out at 8.3 and go from 8.3 down to 0. It starts out at 0, just like any other current, and it's going to go and build. What you need to understand with any transformer is that the secondary side, whatever I place over here, is going to go and control the amount of current that's pulled in there. Therefore, it's also going to control the amount of current that is going to be pulled in this side. And as I pull more currents on this side, I'm also going to pull more current on this side. And this side, my primary, will always just be a reflection of that, whether it's in a step up or a step down application. We're going to just draw a bigger, better graph for this one, then we're going to move on to our last set that we have for this. We'll shrink it. We've already done the math for that one, so we're not too concerned about keeping that one there. Let's just go and draw these ones out over here as being my IP and then my IS that I'm going to go and have. We saw that my current on the primary could start out at 0 and that it ranged across all the way up to an absolute maximum of 8.3 amps. I saw that at the same time, through the beauty of transformer action, the fact that I'm getting a larger reflection over here on this side, that I could go and get a current that would once again start at 0, but would now travel all the way up to 227 amperes, right? Both of these start at 0 amps and 0 amps. And all that we see is that we are going to go and get a reflection. In other words, if I were halfway up my amps on this side, I would also have to be halfway up my amps on this side over here, right? I'd be sitting about 110, 113-ish amps over here, we'll call it, which would mean that I would be sitting at, 4.1 over here on this side. It's still going to go and follow the same transformer ratios all the way through from one over to the other. It's super important to understand that it also operates on both the high voltage side as well as on the low voltage side. In other words, if I could take a transformer and I could feed out a low voltage, I could also take the same transformer, reverse it, and feed in with a low value of voltage, and get out a high value of voltage, right? Now I can make my source, this side over here, the 440, and I could get 12 kV out on this side, and that 12 kV I could go and place across some resistance over there. I'm still going to follow the same thing. I'm just going to go and interchange their values, right? Now all it's going to be is that my secondary is this rating, the 12 kV rating, which ranges between a value of 0 to 8.3 amps, that's maximum, and this one over here is going to go and have its maximum of 227 amps. Once again, based upon what I have connected in my secondary side here. The secondary load is going to go and cause secondary current, which is then going to get translated across to my primary side. In this case, we would be doing a step-up application, going from 440 on our primary up to 12 kV on our secondary. Once again, if I was halfway up on my secondary side, we'll call that 4.1 amps, I would see that I would be halfway up on my primary side, 113. If I'm all the way down on my secondary side, I've got to open at 0. I'm also going to be 0 on my primary. If I have got a really low value of resistance, we'll draw two resistors in parallel to drop our resistance here. If I was a really low value of resistance, I was at my 8.3, my maximum amount of current on my secondary. I would also be at my maximum amount of current on my primary over here. Okay? Understand that this side here and this side here are related via the transformer ratio. TX is short for transformer. Transformer ratio relates them, but then we just use them to go and make either a smaller or a larger reflection, but they move at the same time. All right, let's take a look at number 7. Transformers rated at 2400 volts, 50 kVA. The maximum rated secondary current is 104 amps. What is the secondary voltage rating? So over here, they have not told us what the voltage is. They just told us that that secondary can take 104 amps, but they've given us the VA. First of all, this is an insane example over here. So here for you to go and practice doing your calculations, but in the field, we would not have this. We get transformers that give us voltage ratings, and they give us VA ratings. We don't have, a kVA and a current one. But whatever, we can do the calculation because we know that VA in is equal to VA out. Each side is good for 50 kVA. If I have got a amperage here on my secondary, I can just divide the amps out of the VA, which leaves me with the voltage, which would become 480 volts. All right, do those transformer ratio questions, your self-test. Do the ones that you got as well in any other supplemental worksheets. And then if you're still bored, Google up a bunch. Get real good at making transformer calculations. You're going to have to do some.